Hi everyone, I'm Sherar Shaukat and this is my video for my YouTube channel, and this time around I will be going through different string matching algorithm. So let's begin. So here it's my string matching app, and I have different type of algorithm from brute force, finite automata, KMP algorithm, Robin Karp, Boyer Moores and Orspool algorithm. These algorithm requires pre-processing of text. We will be discussing about these later one by one. Finite automata, here we have to build a state table, KMP. In Robin Karp algorithm we have to do hashing. Hashing is required in order to pre-process the text, so the matching can be done in linear time. So first of all we will check the brute force. So here's my application. It's the number of characters, the number of different alphabet you want in the text, the length of the text, and to generate the random text. So in the first case I will choose 3 different alphabet in my text. Let the length be 20 and generate the text please for me. Yes, yeah, generated the text, and I want to pattern this one. Suppose I want to pattern this. So yeah, pattern, its length is 20, pattern's length is 6, and I'm using brute force and I have to compute. So text, pattern, number of iteration, number of comparison, match found at 5. So it matched the pattern. So brute force takes the complexity, the time complexity for this algorithm is a quadratic n square, or we can have, or let's check the complexity first, how it works. So for the brute force, where n is the length of the text, yes, and let suppose m, and take m is the length of the pattern, so time complexity comes out big O of n into n minus m plus 1. So it's the time complexity of the brute force. It's obvious, everyone knows. One question for my user: do you know the first linear time string matching algorithm is given by whom? If you don't know, you can Google, or I will be telling you that Maurice Pratt has given it in linear time. First time has given the string matching algorithm in linear time. So let's discuss more about the brute force. So it's good for when the number of alphabets, number of characters is less in my text. But suppose, what is the worst case? Let's check it, the worst case of this algorithm. Suppose I have a text like this. Text, the number of characters 2, then it will automatically decide, and I have to check for the pattern B. Let's compute it. See, the number of iteration is 13. It will be n minus m, where n is the number length of that text and m is the length of the pattern. So n minus m, number of comparison, heck, horizon, rise, a huge rise in number of comparison, match found at 12. It's obvious. Suppose I have I make it a, again a, and I check for this one. What does it give the result? It's obvious, the match was obvious that it will be matching at every index, but see the number of comparison, it's increasing quadratically because the time complexity is n. It's the worst case scenario for this algorithm. And if I have chosen used a finite automata, it's need a pre-processing of text. It build a state table Let's check for this particular case what the number of comparison. We are more interested in number of comparison. So compute. So it had built a state table, and see the number of comparison 17, where in the last case where we have a number of comparison 60, when we have used a brute force. See, again I can make it like this. If I use this one, see, I have used in compute number of comparison 46, match found at 14, and if I use in a finite automata, it has built a state table for us, and the number of comparison 17. So finite automata is a better alternative. Of course it's a better alternative. It's neither pre-processing of text. It builds a state table, and for building a state table you need the algorithm. There are two type of algorithm in which to build a state table, it's the time complexity comes in the quadratic, and I will be discussing later. So it is the worst case scenario for the algorithm brute force. So let's see the finite automata, how it works, and how it works, how it pre-processes the text. So here we have, where's my notepad here? File. So I have a pattern A B, AC, and A. The pattern, its length 7. It's starting from index 0 to 6. So we have to build this state table. So this state table is required for matching, and if we have built this state table, the matching will be very easy, and it will be take a linear time to match. So this is a state, and how to build this state table, let's see. So it's we are in at start, we are in a state 0, and to go to the state 1 we need a A, and if we get a A, we are at state 1. So from state 1 to state 2 we need a B. If we get a B, we are in state 2. Damn good, so easy. From state 2 to state 3, and if we get a A again in state 1, we are back to the state 1. We are not going anywhere else. We are back to the state 1 if we get a A here. From state 2 to go to state 3, we need again a A. From state 3, and if we get a A in a state 3, we are back again to state 1. We are back again to the state 1. So from state 3 to state 4 we need a B. To go to the state B we need again a A. From state 5 to state 6, if you want to go to state 6, we need a C. And suppose if we are in state 5 and if we get a A here, we are going back to 1. We get a A. Or if we get a B here, we are going back to 4. State 4. Simple as that. And after to last stage, if we need a perfect A, back. And from state 7, it's the last stage. We can go, if we get again A, we can go again to state. If we get a B, we can go to state 2. We get a B here. So we have to build this state table, and to build this state table there's two algorithms present. First algorithm requires big O of time complexity to build this state table is M cube, where M is the length of the pattern times number of different characters, where number of different characters means number of different alphabet A, B, C. If we have 3 alphabets, number of different alphabet in our pattern, then it will be 3. So if we have 4 different A, B, C, D, then it will be 4. So different number of different alphabets. There is another efficient way to build this state table. Its time complexity is m into number of different alphabets. Same. So what is here? So we have to build this. So let's first of all check the finite automata. So I want a 3. Let be 20. Generate the text for me. I generated a text. I want this pattern to be. I suppose I want C. I want to search this one for this case. Compute. Let's see. So number of iteration 20, number of comparison 20, because it's taking a linear time. It depends upon the length. Match found at index 5 and 7. Cool. And it build a state table. A, B, C. Similarly, we want to go to. If we get a C, we go to state 1 from 0 to 1. If we get again a A, we go to state 2. And in the same time, if we get a B here, we again go to state 0. If we get a 1, we remain at state 1. Similarly, if we get a A here, we go back to the state 0, B 0, 3. Finally, we reach the final state. Bingo, and the string has been matched. So let's check the case that we have discussed. We have discussed the case of A, B, A, B, A, C, A, and make a random thing. C, 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 A, B, C, C, A, and B, B, C, A. It's a random thing, but I've taken this one. Let's compute it. Yes. Match found at number of iteration 21, comparison 21, match found at 6. It built a state table. The state table will be the same that we have discussed here. Wait a minute. I just adjust the screen for you where you can easily make it out. See, 0, 1 for the state 0. If we get a A here, we go well and good, we go to the state 1. B, if we get a B in first character of match, we are in state 0. We are in state 0. In the case of C, we again get A. So the state table is same. Straight. So to build this state table, we need if we use this algorithm, we have to pre-process the string. So in the next part of my lecture, a tutorial, whatever you can call, a brief idea, a brief overview of this algorithm, I will be discussing about the algorithm, the code, and the KMP algorithm, Robin Carhart, where you have to build the suffix table, suffix function in hashing. It includes hashing. So in the next part of the video, I will be discussing about these things. Thank you for watching.